So, welcome to this new lecture of solar photovoltaics principles, technologies and materials, and we were discussing this PN junction analysis in light. So, before we go to the continuation of previous lecture, we will just recap the previous lecture. So, in the previous lectures we started our discussion on we started our discussion on PN junction analysis in light, and in these conditions what we want to calculate is Jn at minus Wp plus Jp at plus Wn plus JSCR, because this JSCR is now finite because you have certain amount of recombination as well as generation within the semiconductor. And we also made various other assumptions to calculate currents, and basically we needed to solve the minority carrier equations. The carrier equations were del 2 Np by del x square minus delta Np divided by, so you can say Np minus Np naught divided by ln square plus G Ex divided by dn. So, sorry, let me, so this should be E x divided by dn is equal to 0, and then we looked at del 2 Pn del x2 minus Pn naught divided by Lp square plus Gex divided by dp, that is equal to 0. So, one is for electrons and another is for holes, both are minority carriers, and where we looked at Gex, or I think it was small Gex, which was equal to 1 minus Re into alpha E into Ise, which is the incident radiation, into 8 to the power minus alpha x. These were the equations with which we started, and we also made certain boundary conditions, and those boundary conditions were at x is equal to minus xp as well as x is equal to xn, and then the boundary conditions were at x is equal to wn and x is equal to minus wp. So, at x is equal to minus xp and xn we considered the surface recombination into account, whereas x is equal to wn and minus wp we just took the same concentration of carriers as we took earlier, and that was Ni square divided by Nd exponential of QVA minus by kT minus 1 for whole concentration, and for electrons it was Ni square divided by Na into exponential to the power QV by kT minus 1. So, this was these were the things that we did, and if you look at those expressions, we said in the last, go back to the previous lecture. So, we looked at these expressions for electrons and holes, and what we came up with these were something like these. So, we had these electron concentration, the electron current at minus Wp as a function of energy, and then hole current at plus Wn, and what we got was we had two different. So, this was what the differential equations, and when we substituted these carrier concentrations into these differential equations, what we got is the current, and this current is basically, you can see there is a bias dependent term, there is a illumination dependent term, both are independent of each other. So, one depends upon the incident radiation and second depends upon the bias. Similarly, here one depends upon the incident radiation, another depends upon the bias. So, this is Is here in both the terms. Similarly, you have QV by kT. So, obviously, if you make the I equal to 0, it should take us back to the PN junction in dark. So, that should be doable. So, I will leave that to you exercise, that what happens when you take when you make the illumination equal to 0, then PN junction should work like a PN junction in dark. So, this is what the total current was, and then we did these analysis for SCR current. The SCR current, since there is generation, we have a generation current, and we have a recombination, we have a recombination current, and mathematical sum of these two will give us the SCR current. SCR current is the current because of recombination minus the current because of generation. So, generation current will be negative, whereas recombination current will be positive. So basically in the light total current is Jn at minus Wp plus Jp at plus Wn plus Jscr, and this is what is total current, which is simplified by making a few assumptions to make them suited to the practical solar cell diodes. And we will now get back to our current lectures this thing. So in the current lecture we look at a few special cases to solve these equations. Okay. So the first special case that we look at is p-n junction in dark, that is at equilibrium. So of course Is is equal to 0, Va is equal to 0, which means J should also be equal to 0, which is perfectly fine, and if you do that you will find that. And then of course Px is equal to Na and Nx is equal to N naught for x less than minus Wp, and Nx is equal to Nd and Px is equal to P naught, that is. So this is on the P side and this is on the N side. So basically it should look like a p-n junction in dark at equilibrium without any bias and without any illumination. So both the equations which I showed you earlier, they should boil down to this. And of course between xp and between Wp and Wn, Np is equal to Ni square. So basically no minority currents in the neutral region and no net recombination in space charge region. That is what the assumption was. Now if you have a p-n junction in dark under applied bias, then of course Is is equal to 0, that is the illumination term vanishes. So there is no illumination term, what we are left with is only the current term. So there is a net flow, since you have a bias, which means the moment you have bias you have situations like in the previous case basically there was no bias, but now you have a bias. So if you look at the p-n junction, the p-n junction has a profile like this. So when you have no bias, then Fermi levels are aligned and you have a built-in field, alright. When you apply bias, for positive bias it becomes Vbi minus Va, which means the Fermi levels are also split. So when the bias is applied, these Fermi levels are, so if I use a different color, so when the bias is applied, the levels become something like these, alright. So okay, and here also it will increase by certain level. So essentially this bias has now reduced to Vbi minus Va, which means the Fermi levels also, you can see that there is a shift in Fermi levels also. Fermi levels are going to split. So since the energy levels have risen on this side, the N Fermi level goes here and P Fermi level goes here. So there is a split, and the split is equal to the applied bias, alright. So basically the Fermi levels are split, and this split is nothing but equal to Va. So now there is a split in the Fermi levels. As a result you will have, so what you will do is that your J dark as a consequence of diffusion will be equal to Jn minus Wp plus Jp at Wn. Considering, and we also consider that N side and P sides are thicker than, so considering that P and N sides are thicker than Ln and Lp, which means the semiconductor diode is thicker than the diffusion distance of minority carriers. As a result, surface recombination becomes irrelevant because the carriers will recombine by the time they reach the surface. Okay, so it's a basically long based diode. You can say diode is pretty long. As a result, you can write for x greater than Wn, your Pn minus Pn naught is equal to Pn naught into exponential of Qv by Kt minus 1 into exponential of minus x minus Wn divided by Lp. This is for, this can be, so the previous equations are simplified now. Okay. So since surface recombination is irrelevant, we make Sn and Sp equal to 0. So when you put these conditions into the previous equations, the detailed equations that we showed earlier, then we get this delta Pn as this and delta Np as this. So you can see that there is a bias dependence, plus there is some exponential dependence depending upon the junction, which depends upon the Wn, Wp and the position at which you want to take the current. This gives you, from these you can work out what is Jn at minus Wp and Jp at Wn, because they are diffusive currents. So you just have to plug this in. So basically the current is nothing but minus plus or minus Q d dn slash p divided by dx. So depending upon whether you have positive or negative charge, you just work out the current by differentiating this, and you will get these expressions. Okay. So, when you get these expressions, these are similar to what you get for a PN junction in dark. So, Jn at minus Wp is nothing but Qni square Dn divided by Na ln into exponential Qv by Kt minus 1, the similar expression except that you have P replaced by N and A replaced by D, you get for Jp, and if you sum these together you will get the same current as you get in PN junction in dark. So, this is the dark current in PN junction, which is as a result of diffusion. Alright. Now, so hence we can say that J diff is equal to Jn at minus Wn, Jn at minus Wp plus Jp at Wn, which is equal to J naught diffusion into exponential Qv by Kt minus 1, and J naught is this. So, this is what we expected from diffusion current, but what happens in solar cells is that although we were assuming earlier that there is no recombination current in space charge region, there is a recombination current in space charge region because the Fermi levels are now split. Okay, when the Fermi levels are split, so because your semiconductor is like this. Okay, so this is your PN junction, right. So, this is P side, this is N side. If I take it for electrons, the Fermi levels will go in this fashion, and holes Fermi level will go in this fashion, and there is a split in the Fermi level. So, the intrinsic Fermi level goes like this, but within this region also, since you have Fermi levels going across like this, you have a split in the Fermi level within the. So, remember this is the junction, right. So, within this also you have a change in the, since the Fermi levels are now, so these Fermi levels, so you have a Fermi level for, so this is EF, you can say P, this is EF N, and because of this split of Fermi level within these space charge region, you have, because remember this is also P type, right, although it is a depletion region, it is a P type semiconductor, and this is N type semiconductor, and these Fermi levels will also. So, what we are showing here is the splitting of the continuity of EI, but EI is irrelevant, right. So, it will, so you will have this EFP continuing in some manner, EFN continuing in certain manner. So, the exact nature we cannot depict here very clearly, but you are going to have certain split of Fermi level because of applied bias. Now, if you have certain split of Fermi level applied bias, and the fact that you have electrons migrating from one side to another and holes migrating on another side to another, there is always a possibility of recombination within this region. Okay. So, when you have electrons going from here to here, holes going from here to here, the recombination, there is certain amount of recombination in the space charge region, and this space charge region recombination gives rise to what we call as space charge current, which we ignored in the PN junction and dark analysis earlier. So, in the context of solar cells and practical devices, we do have to consider this, and it turns out that this current actually has a dependence of exponential of Qb by 2 Kt instead of exponential of Qb by Kt. So, this is sort of non-ideality in the PN junction diode that we observe. All right. So, when you, for example, if you just plot it as a function of log of current versus voltage, the slope should be equal to Q by Kt, right, but what we get is the slope is equal to Q by 2 Kt for a non-ideal diode. Often the behavior is mixed, and this is the current, which is the space charge current pre-exponential factor, which is Qni into Wn plus Wp divided by square root of tau and tau p, and this is from the same current, that same SCR current that we got. So, this is the SCR current that we invoked when we said ki bhai, that now you have PN junction which has effect of both, the PN junction which has a SCR in which recombination and generation is a possibility. Okay. Earlier we ignored this in our PN junction analysis. So, now if we do not ignore this, then we have to consider this space charge region current. So, within that expression that we looked at the last lecture, if you made the illumination term 0, then only the recombination term remains, and the recombination term that remains gives you this space charge current, which is essentially, you can say, a dark recombination current. All right, and this has a factor of Qb by 2 Kt. So, in addition to dark current that you have here, there is extra dark current which is here, okay, which has a factor of QV by 2 kT, which is because of space charge recombination, which was ignored earlier. So if you combine all the two things together, so J dark has a diffusive component, this is the diffusive component, this is the space charge component, and there is another component that we have added here, which is because of radiative recombination, which will always occur. Okay, radiative recombination is present in all the semiconductors. As a result, especially in the direct band gap semiconductor, radiative recombination is very prominent. So another term which is added ad hoc, whose dependence goes as QV by kT minus 1. So there are three components of dark current. One is the diffusion current, another is the space charge current, third is the, so this is for diffusion that we took for similar p-n junction analysis. This is space charge recombination, and this is space charge region recombination, and this is radiative recombination, which will always be present in a semiconductor, whose extent will be determined by whether it is a direct band gap semiconductor or indirect band gaps. So this term is prominent for direct band gap semiconductors. Okay. So for indirect band gap semiconductors, generally Ln and Lp are much larger than Wn and Wp, and as a result so for indirect semiconductor like silicon, the dark current is generally so when the diffusion distances of carriers are longer, which means they can be alive for longer distances, as a result they do not recombine too much in space charge region, and even the radiative recombination is smaller in direct band gap semiconductors anyway, because you have to have a phonon assistance there, and that does not enable the recombination very easily. So these two terms are not so prominent for indirect band gap semiconductors, which have longer hole and electron minority carrier lifetimes, as a result longer diffusion lengths. So in this case only the diffusion related dark current persists. So you will see in the dark data the dependence will be QV by kT for that. So there are less recombination losses and negligible radiative recombination for a indirect band gap semiconductor, provided your diffusion distances are large. However, for direct band gap semiconductors which have high absorption and wide space charge region, they generally have very wide space charge region. These materials generally have a dark current which has QV by 2 kT dependence. So this space charge recombination is higher in these materials, especially when you have direct band gap semiconductors. But generally it is not always very ideal. So if you have more than one processes active, then we generally say that J dark is equal to J naught into exponential divided by exponential of QV divided by mkt minus 1, where m is the ideality factor. So we say if m is greater than 1, then obviously it leads to non-ideal diode, and that reduces the fill factor of the device as well because of increased recombination. Okay. So basically you can say that increase in this m factor of more than 1 often leads to more recombination losses, as a result less current and less photocurrent that you get, and less fill factor of the devices. So if I now plot, let us say J dark, this is at log scale as a function of V. Okay. So if I draw only for diffusion current, then for diffusion current the slope should be like this, right. This is for diffusion current which has a slope of 1, or for which m is equal to 1, right. And if you have a space charge current, the space charge current will, so this is diffusion and this is space charge assisted. In this case the slope is equal to half, right, because in one case you have, so in this case m will be equal to 2. Generally what we observe is we have a trend like this. So we have at the smaller voltages we have space charge recombination. When all the traps are filled, then it goes to diffusion current. This typically happens at lower voltages. Okay. So at lower voltages you will have space charge current recombination when the slope will be half, and at higher voltages when all the traps are filled, recombination reduces. As a result, the carriers move away from the junction. However, if you now what is likely to happen if suppose carrier lifetime decreases? If carrier lifetime decreases, in that case the space charge recombination will become more and more. So, if the carrier recombination increases, this curve tends to shift to the, so it will shift to up or down, it will shift in this direction. So, if your carrier recombination increases, it tends to go up. So, this will go up if you decrease the carrier lifetime. So, when the carrier lifetime reduces, then of course recombination is larger. As a result, recombination current dominates over the diffusion current. Okay. So, you will obtain, so basically your dark current will also be dominated by recombination than the diffusion current. So, this is, so basically the shift that happens, the shift happens at higher voltages. So, you can see that V transition is higher in, so V transition 1 is higher with respect to Vt or prime. So, Vt prime is greater than at Vt because tau prime is smaller than tau. Okay. So, this is what happens, is observed in semiconductors. Now, let us look at p-n junction in equilibrium. So, this is what you will observe in a p-n junction, in a real p-n junction under dark. You will not obtain always a slope of 1, it is likely that you will obtain a slope of 1 by 2 because of recombination, which we earlier ignored in our p-n junction analysis. And this is deviation from ideality, because now we are saying that there is a recombination in space charge region, whereas earlier assumption was that space charge region had no generation and no recombination. So, of course, there is no generation, but there is recombination. Okay. Now, let us look at this condition of p-n junction under illumination. So, when you have p-n junction under illumination, then what we create is then we create conditions which are called as non-equilibrium condition. Non-equilibrium conditions because you suddenly flood the semiconductor with a lot of carriers and energy levels move up and down. So, Fermi levels, for example, both N and P concentrations increase rapidly within the semiconductor, and as a result you have huge increase in the carrier density on both sides. So, what will happen in this case is, so if you plot the carrier density, for example, the carrier density if you plot, suppose this is a junction. So, this is let us say carrier density N or P per cc, and this is distance x. You will see that on P side you will have large P, but you will also have large N, whereas earlier N was, if you plotted at equilibrium, this N would have been at very low level, right, somewhere like that. Similarly, on the N side, this carrier density would be very large, and this would be very increased on the P side as well, whereas it was in case of the device when it was in dark, this would be the behavior. So, this would be the carrier density N, and this would be, so this would be Nn, this would be Np, this would be Pp, and this would be Pn. So, Pn increases, Np increases, and of course, there is a change in Pp and Pn as well. So, minority carrier concentration suddenly increases a lot, okay, a lot. So, there are major energy shifts within the semiconductor, and those energy shifts within the semiconductor give rise to large, we can say, a negative current in the semiconductor, because remember in the p-n junction, in the forward bias, we are looking at the current which is, so you have hole diffusion from P to N side and you have electron diffusion from N to P side. So, you have a certain current sign in this case. What will happen in this case is, if you now look at from the sign of current, since the sign of current, generation current in this is the current which is produced at 0 bias, okay. So, we are looking at the condition first at 0 bias. So, when you have 0 bias, then the current starts flowing in the opposite direction. You have large negative current, which means negative current will mean you have large flow of holes from N to P side. because you have sudden increase in the hole concentration on this side. Similarly, you have large electron current from one side to another. So you have flow of carriers, because you can see that for electrons to go from this side to that side, they still have to face a barrier, right? Because there is no bias. There is no bias. So if you look at the Fermi level, if you look at the energy situation, if I can maybe insert a slide here, I'll come back to the slide again. So if I just draw the energy band diagram, so let's say this is at 0 and this is your EC, and this EC is like this, and this is okay. So we are having V is equal to 0, but IS is not equal to 0. So this condition is called as short circuit condition, all right. So in this short circuit condition, what will happen is that since you have of course increased the hole concentration, so hole concentration will obviously be increased. So there is certain PP, but you also have large increase in NP, which means the quasi Fermi level that corresponds to electrons will increase here. So this is EFN. So if I just plot it like this EFN will be something like that. So this is EFN. Similarly, you will have quasi Fermi level for hole. So this is EFP. So this is Fermi level corresponding to holes on the N side, because on this side the hole concentration also will increase, okay. So this increase in the hole concentration on P side, N side, and this increase in the electron concentration on the N side leads to a raising of Fermi level or quasi Fermi levels corresponding to electrons and holes closer to conduction and valence band. So now you can see that electrons from this side, if there are a lot of electrons on this side, they can jump from here to here. Similarly, if there are a lot of holes from this side, despite having a diffusion gradient, despite having more number of holes on this side, there is a driving force because of splitting of Fermi levels, because Fermi levels produces a inbuilt force for these holes to migrate from this side. So electrons will come this side, holes will go this side. This is the flow of electrons and holes in the opposite direction, and this contributes to what we call as negative current at zero bias. And this happens because of splitting of Fermi levels, because the Fermi levels for electrons on P side is very high, Fermi levels for holes on N side is very high, and these splitting of Fermi levels provide driving force for electrons to move from P to N side, contrary to popular wisdom, right. You would assume normally the diffusion to take place along the diffusion gradient, but this is not diffusion gradient, you can say this is the sort of potential gradient or chemical potential gradient. So now this is, in some sense, it is called as uphill diffusion, and this diffusion is happening because of gradient in the Fermi energy for electrons and gradient in the Fermi energy for holes. So holes go from N to P side and electrons go from P to N side. As you increase the bias, slowly and slowly more electrons will go from this side to this side, holes will go from this side to that side, and they start countering this, and that is what happens in the solar cells. As you increase the bias, the current decreases, the current starts becoming from more negative to less negative, and eventually it goes to 0. So that is what happens. So which means your forward current keeps increasing, the bias induced current that starts taking over the current that is produced by chemical potential gradient as a result of splitting of Fermi level. So essentially, if I go to now previous slide, we are saying that short circuit condition means V is equal to 0. There is no net recombination in space charge region. The JSC is equal to Jn at minus Wp plus Jp at Wn plus J generation current. This generation current will start dominating, and the net photocurrent is now equal to integration from 0 to infinity. So, you can do it from 0 to infinity, although you can do it from Eg to infinity also. So, this is JSC for a spectral current, you need to integrate for all the energies. Okay. So, we will look at these expressions in the next lecture because we are running out of time. So, essentially the purpose was to show how you get large photocurrent which is negative in sign when you have 0 bias and illumination on. We will dwell on this further looking at these expressions which are in front of you in the next lecture. Okay. Thank you.